We are now ready for a formal definition of how to fold in side information into the chance process. Recall now that our experience with simple examples tells us that the way we proceed is always by providing information in the form of the occurrence of an ancillary event, let's say B. We have a target event A of primary interest to us, and a Venn diagram encapsulates the picture quite nicely. So we have a target event and an ancillary event. And now what matters, given that the ancillary event has occurred, is proportionately that portion of the target event which resides in the ancillary event. Now let's formalize this. We will say the conditional probability of the target event A given the occurrence of an ancillary event B of positive probability. In short, that's a mouthful, so we'll simply say the probability of A given B. We will denote it succinctly, mathematically, by using a ball font P for probability, as always, the target event A of interest to us, a vertical bar as a separator to tell us that there is information arising, coming from an ancillary event which follows the bar that is B. We are taking some liberties with notation here because, of course, P stands for a probability measure. It is a set function. The moment you see P, you anticipate an argument which is a set, an event. And now I'm giving you two events with a bar in between. But it's a harmless liberty. We take this object to mean something very specific. Colloquially, the proportionate part of A that resides in B. And formally, we define the conditional probability of A given B to be the ratio of the probability of the intersection of A and B to the probability of B. Before we go on to test our understanding and build more intuition for what this definition is telling us, we should extract some immediate features from this very simple definition. First, the chance or the probability of B arises in the denominator, and from early calculus we know that dividing by 0 is forbidden. The event B has to have strictly positive probability. What if B has 0 probability? Well, in this case, a conditional probability is simply undefined. In most elementary settings, we will never encounter the situation where we have an event of 0 probability. But when you do move into the continuum, we will find that there are non-trivial events of 0 probability. And in those instances, we are going to have to adapt this definition to do something else with it. But for our purposes now, we will define conditional probabilities of events only when the side information is in the form of an event of strictly positive probability. Now, the events A and B I've given you here are arbitrary events in some common probability space. We put no restriction on the nature of these events. They are subsets of the sample space. And in particular, the ancillary event, the side information B, could arise or could be specified in any fashion whatsoever. So, for example, B could be formed from intersections, unions, other set operations on other events. B could be a composite event. It makes little matter. At the end of the day, we have a subset, and we're conditioning on the occurrence of that subset. One final feature we should extract from the story is that, again, we have two events, A and B. What if we reverse their order? What if B becomes a target event, and we're given ancillary information, side information, in the form of the occurrence of A? The definition will immediately tell us that, in general, conditional probabilities are not symmetric with respect to the order of specification of these events. In general, the probability of B given A is not the same as the probability of A given B. To settle understanding, write down what the probability of B given A is, and then ask yourself, under what conditions can the two conditional probabilities be the same? Pause and see if you write it down. Let's see if you came up with these answers. The probability of B given A. Recall the definition says the way we write down a conditional probability is in the numerator you write down the intersection probability. In the denominator you write down the probability of the ancillary event, the side information. And so the probability of B given A is a ratio of the probability of B intersection A to the probability of A. Now, if you look at the two formulae, you find that they're not the same. The numerators are indeed the same. Intersection is a commutative operator. You can do it in any order. So the chance of A intersection B is the same as the chance of B intersection A. But the denominators are rather different. In general, A and B need not have the same probability. It's indicated visually in your figure where I've shown you A and B having different sizes and shapes. But when can these two ratios be the same? Well, the necessary and sufficient condition is immediately that the denominators have to be the same, and therefore the probability of B given A is equal to the probability of A given B if and only if A and B have the same probability. We're not saying that A and B are the same events. We just say that they have the same probability. Okay, now we have a definition under our belts. We should immediately, to settle concepts, test our understanding of the definition.